Days are numbers, count the stars. It's the first line from a popular song, but the one after is more relevant. We can only see so far, it says, and it sums up perfectly our relationship with the stars that matter so much in our lives. What is a star in the first place? Well, a star is to the cosmos what a key player is to a team, a ball of energy just waiting to be unleashed. Stars are essentially bodies of hot gas arising within a nebula, which itself is simply a cloud of dust and gas within a galaxy. Most famous perhaps is the Eagle Nebula, with its stunning pillars of creation. Each nebula is like a cosmic kindergarten, from which bright young things are just bursting to escape. We call them stars. Suggestions are that 7 new stars form each year within our Milky Way alone. What trips the wire to kick-start the formation of a star? Usually it will be one of 3 events. The effect of an explosion from a nearby supernova, the nebulas moving through a particularly crowded pocket of space, or a flirtation with another passing star. At some stage, an area of high density within a nebula will resolve itself into a globule of gas and dust, which will then contract under the force of its own gravity. This condensing matter heats up. As the density increases, this protostar, that is to say the first iteration of the new heavenly body, starts spinning around a central axis. A new star exists in what scientists call hydrostatic equilibrium. The inward force of gravity is balanced by the outward pressure from the star's core. If there is sufficient matter, a nuclear reaction will take place, releasing a huge burst of energy, which must find its way from the new body's core to its surface. This process takes place over an enormous time span through a combination of radiation and convection. Next time you go to the beach, imagine trying to count every grain of sand, not just the ones you see, but all the others below. Then turn that idea on its head and imagine trying to count the stars, all those we see and those we don't. ESA's Gaia telescope is making that seemingly impossible task more like a reality. Its full map of the night sky is due for completion this year, but already preliminary data covering 2 million stars has been released, and the scientific world is very excited.
We want to measure a huge number of stars, where they are and how they are moving. So we can answer 2 questions at the same time. What is the structure of our galaxy, but also how it is evolving, or we can also look back in time. How did the stars move to come into the place where they are now? The mission's technical measurement principle is there are 2 fields of view, 2 cameras basically looking at the sky at a very constant and fixed angle, and it rotates along the sky, so it traces a path along the stars. It then uses these measurements to determine the position of stars relative to each other, and then you can get to extreme accuracies also for the absolute position of these objects. The data comes down to the ESA antennas on the S-track network in Argentina, in Spain and in Australia. From there it goes to Darmstadt, who control the spacecraft, and then it goes to our central data processing hub near Madrid in Spain, which is an ESA center. And from there it goes to the data processing consortium, which then slices it up in different parts and processes this into science products. Our first release will contain positions of 1 billion stars. So that will allow us to look what does the night sky really look like when you would look at in random direction with a telescope which can see very faint stars. And a subset of 2 million stars, we will have the distance and the motion. So that is really the basis for astronomical studies. People can really look into details of these sources and study the behavior of the stars. And in addition, we have light curves for about 3,000 stars, so how they have been varying over time to analyze better the internal structure of these stars.
Eventually, it will plot the position and movement of 1 billion stars in our galaxy, the Milky Way. Astrometrists still have their work cut out, but thanks to Gaia, the job of counting the stars just got a whole lot easier. Something remarkable happened in November 2016. Astronomers discovered a new way of witnessing a star's formation. Adding to the familiar methods of transit, gravitational lensing, and direct imaging, they found a new little friend, quite literally. Chandra, the world's most powerful X-ray telescope, is part of the Great Observatory that includes Kepler and Spitzer. It orbits Earth some 140,000 kilometers out and is capable of fine definition of hot, turbulent areas in space. Little Friend acted as a mirror, deflecting X-rays from Cygnus X3 towards Earth to help astronomers identify stars coming into being. In conjunction with the Smithsonian's Submillimeter Array (SMA) system, it detected carbon monoxide and the outflow of gases, which suggest a new star in formation. This is the first time scientists have been able to use X-rays to peer into a Bok globule, one of the focal points of star formation. The nomenclature of stars derives from their size, which is in part a function of the phase of their life they are going through. A life, incidentally, which may extend to trillions of years. The range goes from red hypergiant at one end of the scale to white dwarf at the other, smaller end. Those at the large end are far larger than our Sun. They may be billions of times greater in volume. Dwarf stars abound. The Sun is a yellow dwarf, for example, with a surface temperature of 5,500 Celsius, while red dwarfs like Proxima Centauri are stars on their way to becoming white dwarfs. What remains of giant stars whose light, put simply, is failing. The process of a star's birth culminates in the fusion of the hydrogen at its core into helium, a process called the main sequence, to which the majority of stars belong. Red dwarfs are not only the most common, they are the most durable. They burn at the low end of the surface temperature range at around 3,500 Celsius. In massive stars, the hydrogen to helium conversion is much faster. Paradoxically, the bigger the star, the shorter its life. How else are stars classified? Basically by two criteria: brightness and color. Stars are catalogued by their magnitude, either apparent or absolute. Apparent magnitude, as its name suggests, refers to the luminosity of stars as seen from Earth. This may vary, of course, according to the mass of the star itself, and especially its distance from us. Absolute magnitude corrects that by establishing the star's luminosity as detected from a standard distance. Paradoxically again, the brightest carry the lowest orders of magnitude. A century ago, working independently on opposite sides of the Atlantic, Hertzsprung and Russell came up with the same basic methodology for classifying stars within a spectroscopic range according to the light generated by their wavelengths. The scale runs from O to M, and, to cite some examples, from the blue of Zeta Puppis to the red of Betelgeuse or Betelgeuse. Made any holiday plans recently? If you're a stargazer, then NASA's own travel bureau may have just the thing for you. While a trip to another world may not be within your budget just yet, astronomers are making us increasingly aware of the heavenly bodies above us and planning on getting us there. When set alongside exotic places like Monaco or Morocco or wherever, the holiday destinations advertised in NASA's graphic travel bureau may not seem too enticing. But they are certainly, to use a travel agency cliché, out of this world. The striking images, genuine postcards from the edge we might call them, include HD 40307G. That's the very down-to-earth name for an exoplanet which astronomers call a super-Earth. One of those revealed by the Kepler Space Telescope on its so-called K2 mission when it bounced back from a mechanical failure in 2014. Could there be at least one planet orbiting every star in the galaxy? Already more than 3,000 of them have been confirmed, with almost the same number awaiting confirmation. The nearest to us is Proxima Centauri b, a mere 4 light-years away from Earth, in the triple star system of Alpha Centauri. Proxima Centauri b, excitingly, is an Earth-sized planet in the star's habitable zone, the distance at which liquid water may form on its surface.
Astronomers have found clear evidence of a planet orbiting the star Proxima Centauri. This alien world is the closest possible abode for life outside the solar system.
The idea of celestial harps is not new, but in real down-to-earth life there is indeed a harps at the center of the search for life elsewhere in our skies. It's ESO's High-Accuracy Radial Velocity Planet Searcher, or HARPS for short, which is a spectrographic instrument attached to the 3.6-meter telescope at La Silla in Chile. Reflecting our connected age, in 2016, ESO invited members of the public to follow live as it embarked on a determined search for proof that circling Proxima Centauri there was, as suspected, an exoplanet. the pale red dot that gave its name to the program. Not just any exoplanet, Proxima b, as it had been labelled, is the likeliest one so far discovered with a chance of playing host to life. In late summer 2016 came the thrilling news. Close examination of the gravitational pull of the exoplanet and its wobble effect on its host produced what ESO calls clear evidence for a potentially habitable world, 1.3 times the size of Earth, and in an 11.2-day orbit around its star. Ultraviolet and X-ray radiation levels on its surface appear high, and the exoplanet is much nearer to its host than we are to our Sun. But ESO next plans to use its forthcoming Extremely Large Telescope, the ELT, and later interstellar probes to get even closer to solving the enigma of Proxima b. Where do stars go when they die? That depends on their size, or rather on their mass. Stars of high mass will follow one of two paths. Nearing the end of their life, as the core of the star collapses, it will give rise to a supernova. The gigantic explosion triggered when the output of energy at its core suddenly ceases. Scientists are predicting that Betelgeuse, the red giant in Orion whose mass may be as much as 20 times that of our Sun, is on its way to a supernova within the next million years. The end product of a supernova will be either a new, different kind of star, or that great unknown, a black hole. On one hand, the core may survive as a neutron star, which may measure the remarkably small diameter of 10 to 20 kilometers. Not only that, but they are of extraordinary density. A teaspoon of their substance would weigh in the millions of tons here on Earth. Neutron stars often act as the lighthouses of the sky as well. Because of their strong magnetic field and fast rotation, they emit polar radiation beams, discernible when the beam is directed towards Earth, just as the beam from a lighthouse will be visible out at sea only in fleeting cyclical movements. The other possible fate for a dying star is to become a black hole. While there is a plurality of objects in our sky, black holes bring us face to face with a singularity, the point at which matter is compressed. The singularity will be either a point of infinite density or adopt the shape of a ring. Either way, its gravitational pull is so strong that nothing, not even light, can resist or escape it. Its boundary is described as the event horizon.
90% of black holes in the universe don't have a lot of hot material orbiting around them. They don't form these accretion disks, and so we can't observe them. Tidal disruption events, where the stellar debris causes the formation of a temporary accretion disk, offers us a way to probe this population of supermassive black holes.
One tool astrophysicists use to stare into the abyss is X-ray reverberation mapping.
X-ray reverberation mapping has been very successful at probing the accretion flow in well-established accretion disk structures, but had never been used to look at tidal disruption events. My collaborator at the University of Maryland and I were having lunch one day, and she says, has anyone ever looked at tidal disruption events with X-ray reverberation mapping? That night, I stayed late at the office and just tried it out on this data from Swift J1644, and much to my surprise, the result was amazing, and I could see that we were looking at the structure of the inner accretion flow around a normally dormant black hole for the first time. It's not like a normal accretion flow in an active galaxy that's a flat disk. This is something that is extremely puffy, very turbulent, and we are measuring flashes of X-ray emission deep within this newly formed accretion disk. Previously, astronomers had thought that the X-ray emission is coming from far out in a jet. But what we're finding with these observations is that the X-ray emission is coming from flares very close to the supermassive black hole. And we can use these observations to probe properties of the black hole itself. For instance, we found that the mass of the black hole is something on the order of 1 million times the mass of the Sun.
The Milky Way, which contains our solar system, is itself part of a so-called local group of galaxies, including, for example, Andromeda, which in turn belong to the Virgo supercluster, 100 million light-years across. When we've had a bump on the head, we say we are seeing stars. Looking at it from an astronomical point of view, the number of stars out there is enough to make anyone's head spin. And that's before we even get to the dark side.